All right, this is a quick lesson on gel electrophoresis. So it's the procedure used to separate and analyze DNA fragments using an electric gel chamber. So there's a specific way you have to do this, and it's the full process of gel electrophoresis is to actually uh, separate DNA pieces. So we're going to cut up the DNA fragments using an enzyme. It's going to cut it up into smaller pieces at very specific fragments, and those are referred to as restriction enzymes. Those fragments will then be loaded up into the gel, which I'll show you in just a second when I get a gel picture up here. DNA has a negative charge, so that when you turn on electrical current, it's going to run towards the positive end of the gel. So I'll show you that in just a minute. And then, of course, the smaller the fragment, the easier it is to travel through the gel, so they move faster and they'll fall towards the bottom. Every person has a different fragment pattern. If you're a relative, you will share some of the fragment patterns. And I will put up the link to Amoeba Sisters on Google Classroom so you can watch that and get another idea of gel electrophoresis. So we're going to cut up the DNA here, and we're going to put it in these wells right here. So we're just putting the fragments, loading them in this gel. This gel is made of agarose, which is kind of a seaweed type jello thing. We'll then attach a power source. The negative side's here, the positive side's down here, and because DNA is negative, it's going to travel down to the positive side. The smaller the fragment, the faster it's going to go down, and so the smaller fragments will be down at the bottom, the bigger fragments will be up here. And the gel will look something like that. Shorter fragments down here and big up there. All right, what can we do with gel electrophoresis? Lots of things, really. We can look at evolutionary relationships, basically comparing our DNA sequences to other DNA sequences. We can see which ones are related. It's a way of pretty much discovering a common ancestor in many ways. So if we look at this one here, the common ancestor, and we can look, okay, what's got the most in common with the common ancestor? We can just count the number of bands. So that this one only has 2 bands in common. This one has 1, 2, 3, 4, 5 bands in common. And this one has 1, 2, 3. So this one is the closest. It's got the most bands in common. So if our common ancestors down here, if you remember the planograms, the first one coming off of here would be number 3. And then the second one coming off here that had most in common was number 4. And then finally this, one would be furthest away from the common ancestors. That'd be number 2. That's a way of looking at gel electrophoresis and determining relationships. All right, so also we can use it for medical diagnoses by looking at who's a carrier, who has a disease, and things like that. So as you can see, these guys have different things in common. So if you're normal, normally you just have 2 bands here in this case. If you're affected, you just got 1 big band up here. And if you're a carrier, you've got a couple of each. So you got this one and this one, but you got some of this one. So you got a bit of each. So that determines diseases and carriers. For forensics, if you committed the crime, how are they going to know? Well, they're going to find your DNA at the crime scene, and they're going to run one of these gels like this. So this is the crime scene DNA. They always run the victims to make sure that it's not the victim's DNA here. And so they can see, okay, this does not look like the victim. So we can rule them out. So it has to be one of the suspects. So we got 2 suspects here. So we can just then compare the 2. And you can see here, these are a match. So this is referred to as DNA fingerprinting. Basically, we're looking at DNA. None of these are genes. So when we were up here looking at medical diagnosis, those were actually disease genes we were looking at. Here, we're not looking at genes, we're looking at DNA that doesn't really code for anything because if you don't have a working gene, you're probably not alive. So this is DNA that doesn't code for anything. And so we'll have this crime scene. This M means markers, or just the size of DNA patterns to just give you an idea how big these DNA patterns are, or these DNA bands are. So here's the crime scene. So we got to find the match there. We can see that there's one here, one there, but not three, so it's not a match. This one doesn't match at all. Here we've got all three bands, so of course that's the right suspect. So we're just really looking for matching bands. That's how you read gels. We can also use it for determining paternity. Are you the father? They always know the mother because she gave birth to the child, but they don't always know the father. But we do look at the mother's DNA for this for a reason. One is we have the child's DNA. That's easy. But remember, a child is half mother, half father. So half of these bands are going to match the mom's, and then the other half is going to match the dad. So in this case, um, we show here in purple the mom's matches, and then in blue here we've got father's matches. So that we know that the male one is the dad of the child. That's basically how gel electrophoresis worked. It's just kind of a quick analysis of that. Watch the Amoeba Sisters if you want a little bit more detail. You should be writing your notes from the Google Classroom on this so that you have at least the first part. And then you're going to go to the Google Classroom note sheet, and it's going to tell you to click a link, and then you're going to do a little playing around with that. And then finally do the Edge Elastic quiz. And remember, you can use your notes on the quiz. And that ends gel electrophoresis.